Welcome to 9.3 more logarithms. But Mr. Lin, when am I ever going to use logarithms? I'm glad you asked. So in this section, we are actually going to have probably one of the best connections to the real world that at least this chapter is going to have. So we're going to be given data, and we're going to need to figure some stuff out about that data. So here we go. Whoop. Oh no, my screen's not big enough. So for our Spark Your Learning, create exponential and logarithmic functions. So Spark Your Learning. The population of a town has grown in recent years since a company moved its headquarters nearby. Whoop. Here's the data. Years since HQ moved, 0, 1, 2, 3, 4. Here's your population, and here's the change in population. So this town anticipates needing to build another elementary school as the population continues to grow. So what mathematical question can you ask about this situation? So you can ask, is there a trend? Is there a mathematical way to predict and or how fast is it growing? How fast will it continue to grow? All these are great questions that a formula would answer. So down here, so it does give us a formula. Function P, blah, 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 models the population town in thousands over 4 years since the company moved to its headquarters. So the ability, if you take one thing away from this entire chapter, it's if you can kind of think of, or if you can remember that there is a way, if there is a given mathematical pattern, if you can, that there is a way that you can take this data and make a formula out of it in order to predict the future, basically. Now, you can never really predict the future, but this is the kind of stuff that you're going to see in science. You're certainly going to see this in the rest of your mathematical career, but like all the sciences. So my chemistry folks know that we've found relationships, we've put the best curved line to it, and then we can make predictions. You'll use this in business. You know, when you're making decisions about how much stuff I should buy versus how much profit do I expect. I mean, some of these businesses, especially like the big, think Boeing, it takes years to make a plane. And so in order to make some of those decisions, they need to be able to predict the future. And you can do that kind of with math. So let's get started. All right, before we jump into this, we got to know a little bit of background. And so if we create an exponential model from a data set, so we have an exponential model. Here's our function. Again, we are using letters. And let's see here. The function value of the next integer value of x is given by f of x plus 1. And so what we got, okay, I'm going to do this here on the side because I think it'll make more sense. Go red because it's awesome. So equals a, b to the x. So if we have a given set of data, we kind of need to understand how this function reacts as x increases. So like as it's x plus 1, x plus 2, whatever. So if we find what f of x plus 1 is, we just plug x plus 1 in for x. So we have a, b, x plus 1. So we also know the rules of exponents. So this is equal to ab to the power of x times b. So this can help us out when we find, so if we have two data points, we can use their relation to each other. If they're off by a factor, that's what that number is going to be. That's what that b is. So increasing x by 1 multiplies the value by b. This means that for successive integer values of x, each value of f of x is b times the value that precedes it. So like x times 2, or if x plus 2, would be ab to the power of x times b, so on and so forth. We can use that relationship to then help build our exponential model. So that's what we're going to do. So if we are given a data set, for example, so here's our data set down here. We've got f of 1, f of 2, f of 3, and then we have our data right there. So we need to build an exponential function based on that. So I've already told you that it's an exponential function, so we know that. So we just need to figure out the base of it. So we can take f of 1 divided by f of 2 to give us that extra b. So you want to do some real quick algebra because it would be kind of fun. So from back up here, if we have f of x equals a b times x, f of x plus 1 equals a b x times b. So if we put them over each other, we have a b power of x over a b power of x times b. We have boop, boop, 1 over b left over. Or we can switch that around, and then we'd have the b on top. So looks like that's probably more so what we should do, right? So we're looking for this b. So instead of putting f of x over f of x plus 1, we should do what they did. Imagine that. And we should do f of 2 on top. So f of 2 over f of 1. So we plug some of these numbers in for those. So we've got 1.125 divided by 1.5. Shove that into your calculator, and you will get 3 over 4. So what are these other numbers here that they're doing? Well, theoretically, you can do it with any consecutive values, right? So you can also do it with f of 2 and f of 3. So if we took f of 3 over f of 2, that's where these numbers came from, then you would also still get 3 over 4. So now we have a general trend that means that our base is going to be 3 over 4. So then we could then come back to our employer or whatever this data, is supposed to mean, and we could say something along the lines of, hey, there's an exponential growth function here, and it's going to look something like that. So now we can then use that to predict. I can now predict f of 4, f of 5, f of 6, f of 7, so on and so forth. And in things like business or science or whatever, that's really important to be able to do. You're predicting the future. So let's try it out. So the table shows the number of newly built housing units sold each year in the United States for the years 2011 through 2017. Boop, 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 boop. So there it all is. Now, since we're kind of sort of in the real world right now, do you think our data is going to be perfect? Hopefully the answer is no, because our data is never perfect. But we still can be able to find the ratios. Again, if I tell you that it is an exponential growth function, or even just an exponential function, period, whether it's growth or decay, you should be able to figure it out. So we can say let h of t represent the number. So then we just find 2 consecutive ones. So this first one, they took 0 and 1. By the way, they defined their t as t equals 0 is 2011. So this would be like 0, 1, 2, 3, 4, 5, 6. Just an FYI. So if we take h of 0 over h of 1, plug that into a calculator, and you will get, well, from our table up here, I did that backwards. We want h of 1 on top and h of 0 on bottom. So then you're going to have 368 over 306, and I just, hey, these numbers are in thousands because they're all in thousands there, so not a big deal. Even you can leave all the zeros in; they're all going to cancel out anyway, so whatever. So we plug that into a calculator, and we get approximately 1.2. We're done, right? We're in the real world, so we should probably do it a couple more times to make sure it's legit, right? So if we take, so we can do 0 and 1. They did 1 and 2. Again, they got this number. They did 3 and 2, 4 and 3, 5 and 4, 6 and 5. But wait a minute. If this is a real exponential growth function, why aren't all of these numbers the same? Well, again, we're in the real world, and to be completely honest, the price of these homes is not dependent on a formula. It's dependent on like market values and stuff like that. So they're not the same, but they're kind of close, right? So again, in science, math, real world, or just the real world, a lot of times if we have something that's similar and we need it to be one number, we'll just take the average. So that's what they did right here. Average is defined by you add everything up and divide it by how many things you have. So in this case, we added up all of our values. Let's zoom in. So we added up all of our values, and we have 6 different values, so we divided by 6. So this gets plugged into your calculator, or the appropriate number of parentheses. You can put that straight into your calculator, and we get this number. But nobody likes decimals, right? Wouldn't it be nice if we could turn it into a fraction? That's a good question. Let's figure out how to do that. So part of this class is kind of sort of learning how to use that wonderful computer that you have called a graphing calculator. And so the graphing calculator can actually convert decimals into fractions for us, which is kind of nice, and it's a thing that I didn't know how to do until now, and I thought it was really cool, and I wish I'd known how to do that earlier. So get out of this. So we're in our normal function, and so we just did all of our calculations. We got 1.125. 1.125. Man, I want to turn that into a fraction. So come up here to math, and you're going to select the fraction one, so it's already highlighted here. You're going to push enter. So this just says turn this into a fraction, and boom, done. Now, of course, real world, you may not get a happy fraction. It may be crazy or weird, but you can always turn it into a fraction like that. So convenient, right? That's how you turn things into a fraction. So we've got 9 over 8. Which is what they got. Move my face. So now that we have our average, we can take this, and our b, or our base, is going to be 9 over 8. We said that 2011 is going to be our t equals 0. And so then if we say things that are in thousands, we've got our equation right here. So 306, which is kind of where we started, 9 over 8 to the power of t. So we came up with that. Now you can take this and you can make a prediction about, how far do we go? about 2018, 19, 20, 21. So if the pattern holds, you can predict newly built housing units or the cost of newly built housing units into the future, which is a really useful thing to be able to do. So if we were to graph it, so each of these individual points are the actual data points, and you'll see that it does kind of appear to be an exponential growth function, but the data points are not exactly on the line, so that's okay. The data points do not have to be precisely on the line, because again, in real life, this is just a general trend. This is not an exact graph of whatever. So yeah, the general trend. So does the exponential model for this data show exponential growth or decay? Explain how you know. It shows exponential growth. I didn't. I know this because b of the exponential function is blank than 1. We'll say greater than 1. I'll put a space in there. Crazy machine. Describe, and I don't want to do that one. So why might you use the average of the ratios to identify the base of the exponential function when the ratios are similar but not all exactly the same? So which answer is the best? I'll let you look over them. So the average of the ratios allows you to use a more representative base when ratios are similar but not the same. The arithmetic mean of the ratios allows you to use a less representative. Why would we want to do that? When the ratios are similar, the average ratio allows you to use a less representative. Why would we want to do that? That seems crazy. The ratios need to be the same to get a representative base, so using the average of ratios would be wrong. Well, the book told us to do it, so it's probably not wrong. So your best answer is going to be this one right here. So the average ratios allows you to use a more representative base as opposed to just picking one or whatever. So that's very, very typical, using the average of something like that. So is the value of a in an exponential model, f of x equals a times b to the power of x, always equivalent to the function value when x equals 0? I don't know. Let's do a little proof. So if we have f of x equals a b to the power of x, and b can be any number. So what do we get whenever we do f of x equals a to the power of b 0? Well, anything to the power of 0 is 1, right? So f of 0 will always equal a. Because b to the power of x equals 0, or b to the power of 0 equals 1, is what I meant to say. Do you think blah is a good model for the data on the table? I'm going to say yes, it is. So it is a bad model? No. Told you, nothing in real life is ever going to be exact. The model is excellent because the curve is an exact fit. Well, that's false because it's not an exact fit. We know that. It is a fairly good model because the curve is less than the actual values for 2012 and 2013, but for the other years, it's a really good representation. It is a bad model because the curve is less than the actual. So again, I think it's a good model. So that's why I like that one right there. I know what you're thinking. You're like, man, we're going to have to find so many of these by hand. It's going to be terrible. Why do we have this, or why do we have this calculator if we never use it, right? Wrong. So create an exponential model using technology. So anytime you guys are ever going to end up doing this, you're going to use some form of technology to make it do your work for you. Typically, it's going to be on a computer program, whatever the company that you work for might prefer to use. In this situation, the company that you work for prefers you to use a graphing calculator. Yours is much better than mine. So we're going to do this using a graphing calculator. You'll notice I rewrote the data points from our last task. Remember the first year was year 0, and then T was 1, 2, 3, 4, 5, 6, and then these are all in thousands, but I just put the first 3 digits there. So you can use a graphing calculator to find the exponential model of best fit for the data set from task 1. Yeah, I'm sure it probably tries to explain how to do it, but let's face it, they're terrible. I mean, let's pull up our graphing calculator, move my face. Okay, so we're going to clear this. So here we go, we've got our graphing calculator. And how are we going to do this? So there's this little button, STAT. I think it stands for like statistical stuff. Probably not statistical stuff, probably just statistics, but whatever. So if you push this, you're going to get into this screen right here. I wonder if I can make it. Whatever. So anyway, you're in this screen right here. So what you can do using this statistics part, you can do a couple of different things. So here's where you're actually going to calculate your regression line or your exponent regressive line. But first we have to enter our data in, right? So if you come here into edit, so it's already highlighted, you're going to push enter. And so I already entered in most of the data, but you have all these lists here. So, like for this one, you can enter any number you want, but we want 0, 1, 2, and so on and so forth, all the way down to 6. And then for each corresponding, make sure you get them right. You enter your corresponding number. So again, 306, 368, 429, so on and so forth. You just enter the and push enter. So if you had more values per T, you could enter all those in if you had them, but we don't, so we don't have to worry about it. So our data is entered. We can go back to our stats thing, and now instead of edit, we want to move over to calculate. So we're going to go, it's CALC, and I've already told you that this is a exponential curve. So you have a hint about which one of these you should use, but you can use, any one of these in the future. But you've got your line regression, AX plus B, your quadratic, your cubic, your quartic regression. So we are looking for an exponential regression right here. So we're going to push enter. So then it's going to ask you which list do you want to use. So for our X list, we want to use L1. This is kind of the default, but again, if you wanted to change it to like L3, you'll see the little L's in the blue ones right here. So you just go L3, but we don't want L3, we want L2. And the rest of this doesn't matter. So then whenever you're ready, you can calculate. So what it does here, number one, it gives us our general formula, y equals a times b to the power of x, and then it gives us our a value, and our B value. So I'm going to go ahead and write those on the screen. So A equals 322.08. And our B, this is our base value, is 1.117. We'll go with that. So then, let's see what they came up with. You can also graph it. I didn't look up how to do that, so you may have to do that yourself. But what is the exponential model of the model of best fit? So it looks like they're rounding to the nearest tenth. So we can say y equals 322.08 times 1. Trying to see if they have one that's close. Yeah, 1, 2 to the power of x. So I just rounded to the hundredths place, not the tenths place, the hundredths place. So there we go. It looks an awful lot like that one. Woo! How does the model compare to the one created in task 1? It just uses decimal points as opposed to a fraction. That's all. If this model continues to represent the relationship, how many newly built housing units would you expect to be sold in 2022? So I'm looking at the original data, and it starts at 2011. So t equals 0 is 2011. So then 2022 would be like t equals 11, right? I'm trying to remember, or I'm trying to do some quick math. 2022 minus 2011, so it's going to be 11. So then you just stick 11 in for x. And that's something that you can then plug into your calculator. Oh geez, there's things all over my screen. No, not second. Whatever. Okay, so let's see here. We've got 322.08, 1.12 to the power of, what did we say, 11? Bam. So we can expect that many thousands because remember we dropped those zeros earlier. That many homes we expect to be built and sold. So that would be like this one. So that's, of course, if the relationship keeps. What they didn't count on is COVID-19. Hashtag welcome to 2020. Okay, task number 3. Create a logarithmic model based on something you already have. So in this situation, we have a biologist who modeled wolf population P versus time. So he started a study at t equals 0, and then for every year, I think it says t is every year, he graphed the population of the wolves, and this is the equation that he got. So gray wolves were reintroduced back in some states, blah, 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 blah. The exponential model shown was developed from a set of data where P is the wolf population at time t in years since tracking began. A researcher studying wolf populations throughout the United States wanted to create a new model that gives the time it takes the wolf population to reach a certain number so that she can compare it to other data. So basically, we have this equation where t is our independent value that you plug in, and then p here is your dependent value that you get. So we want to switch that around. We want to have an equation that equals t. So that's when we're going to start using our logarithms. So this next step is a little bit of trickery. So how are we going to change this into blah, blah, blah equals t? Well, of course, we're going to use logs. And so what they did, and this is where that trickery comes into play. I'm going to move my face, or not. So we've got our p equals 81, 1.09 raised to the power of t. So first we got to get all of this by itself so that we can do something with it. But before we get to that point, we know that we're going to have to do logs somehow. So, what type? So if we did this traditionally, like how we would do it back in our section or the first section of this chapter, we would get p by itself, p over 81 equals 1.09t, and then we'd take log base 1.09 of p over 81 equals t. So log base 1.09 is not a thing that we particularly want, and so the book gave us some trickery that we can do instead. So what they said, or what they did, is they said, oh, so we know that we're going to have to do something with logs, so let's introduce something that will make our lives easier. So they decided to use natural log base e. You can do this with log base 10 as well. I worked it out both ways, and it really doesn't matter, but they chose to use log base e. So if we can turn this part into an exponent that would cancel out with natural log or would work well with natural log, then that's going to help us. So if we want to introduce an e, we could say that e to the power of some number, some constant, is equal to 1.09. So from there, we can take the natural log of both sides. So then natural log of e to the power of c is just c is going to equal the natural log of 1.09. And so now we can rewrite our equation. Come on, zoom in. So you take the natural log of 1.09. That's log 1.09. You do get 0.8617769 blah 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 0.86. So that's what they got right here. So then you can introduce all that back into your original equation, and you have p equals 81 times e to the power of blank raised to the power of t. And so from there, you can just do our algebra. So we've got p equals 81 e to the power of 0.086 t. So we do like we were originally going to do, divide by 81. So we have p over 81 equals e 0.086. Again, raised to the power of t. So then we take the natural log of both sides. So we would have, what would we have? We'd have natural log of p over 81 equals 0.086 times t. So then we would divide by 0.086. So there is an implied 1 right here. So if you shove into your calculator 1 divided by 0.086, then you are going to get this 11.63 natural log of p over 81 equals t, approximately equals t. So that's just a little bit of trickery that they did, this changing 1.09 into an e, because we knew that we were going to have to do that later on, or we knew we were going to have to use the natural log. So that's fine. Again, I can't figure out why they chose e over log base 10, but in the grand scheme of things, it doesn't matter. I did the problem both ways and got similar answers. So whatever, textbook. So let's get my face out of the way again. Face is always in the way. So what was first done to the exponential model? I don't know. The base was converted to e. So this 1.09 was converted to base e. Maybe this will tell us. If your goal is to find the value of a logarithm, it makes sense to start by changing the base to e, especially since this logarithm can be calculated on most calculators. So it's true. What steps isolated t? Select all that applied in terms of p. So we divided both sides by 81. We used the power property. So you can't divide one side by the equation. You can't multiply one side. We use the definition of the natural logarithm and then divided each side by 0.86. We'll go for that. So those are the things that we did. Yay. Okay, so we can get rid of that. So here is the original data that we collected. And so we want to evaluate whether the logarithmic function is a good model for the data using a graphing calculator to graph the data points from the table. Be sure to use the population number for x value, blah, blah, blah. Okay. So we are going to graph the logarithmic function, what we found. So I'm going to write that on the screen. It's going to get a little goofy for a minute, but it's easier for me. 11.63 natural log of p over 81. And we've got all of these points. I don't know if I'm going to plot all of them, but we'll get several of them. So 0, 82, 1, 2, 3, 4, 5. We'll do 5. I'll do 5 points. Show you how to do that. 6 points, I guess. And the rest. I mean, the rest of it is just entering stuff into your calculator. I don't feel like you guys need to watch me do that. So we're going to pull up our calculator. Face in the way. So you should already know how to graph this part, right? Go to y equals, and then just type this in, 11.63 natural log. So we've got a parentheses here, so we're good. Our p is going to be our x, our independent variable that we insert, divided by 81. Okay? And what does our graph look like? That's super zoomed in. So our window, now we'll come back to that. So in order to enter some data points onto that same graph. So earlier in this lesson, we were using these statistics. I think that's what that means. If not, it's the stat button. Okay. So we made a list earlier, by using the edit. So we're going to do the same thing. Hey, that is conveniently not the right data. But this is our list we did earlier. L1, L2, so we've got 0 through 6. I'm going to get rid of 6 because we're not going to do that one. Maybe. Oh, I didn't push enter. Clear, enter. It's not working. Oh, there we go. Got it. So we want 5. Okay, so there's those. The delete button was the one that I was looking for. So, and then I'm looking at this data right here that's on the screen. Again, it's goofy, but you know, life is tough. So anyway, we've got 82, enter, 90, enter, 99, enter, 105, enter, 113, enter, 123, enter, and delete. Okay, start listening again. So in order to get this stuff graphed onto our graph, we are going to go back into our stat or statistics button. And, oh no, I forgot. There it is, okay. So listen again, we're back. So we're gonna go to our stat plot. So again, the way that I got there is second, the y equals button will bring us to our stat plot. And so we want one plot, so we're gonna do that one. So push enter after it's highlighted. So it might look like this when you get on there, but you want to turn it on. We want one stat plot. So our type, it is just going to be a dot, whatever. Now, for our list, remember I entered in L1, I did the time, 0, 1, 2, 3, 4, 5. And L2, I did the 82, 90, whatever. So that's not what we want because we took the inverse. So for our X list, we want that to be L2. And we want our Y list to be L1. So you can choose the marker that you want to use. And then on this fancy one, you can choose what color you want. Blue is fine for me. So we looked at the graph and we couldn't see anything because our window's all screwed up. So let's think about what we got. Our Y values is our time, that's 0 to 12. So we can say our minimum Y is 0. Our maximum, we can just say is 15, so we kind of see it in the middle, and we're good. Our X values, however, still start at 0. It's kind of a nice place to start. Our first value is like 82, 90, 99. Our highest value is 234, 239. So our X max, we could say, is 300. So hopefully. So this is our data points, and this is our graph. So now, and remember, I didn't put all the data points in because you don't really need to see me entering stuff in. But here is the graph. And of course you can change colors and make it all pretty and all that kind of stuff. So this is a really good tool to evaluate whether your data is good data or not, which is what we're going to do. Evaluate whether your logarithmic function is a good model for the data. And so we can say yes, because when we look at our graph, looks similar to this one, the data points follow the line. Now, it's not always exact. You know, you have your little outliers there, and that's fine. That's real life. That's real world. But it's a pretty good estimated curve. So if the logarithmic model continues to represent the growth of the wolf population, after how many years would you expect the wolf population to reach 300? So you can just look at your graph, and your population's down here. Oh, it only goes up to 250. I guess we'll have to use our own graph. So we can just trace. Boop, 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 boop. Oh no, it's just tracing. Our trace function is tracing the list and not the function. So that's fine. We'll just go in and turn this off for a moment. So we need to figure out when our x is going to equal around 300. I'm looking at this number right here, and I'm just going, going, going. Oh no! 300, so our y is going to be 15.2, so I would say about 15 years. Approximately 15 years. Do you think logarithmic model is a good fit for the date? Yes, because the graph model is close to many of the points. I'll go with that. Yes, because the points fall on either side of the graph. So again, we're just looking at our points versus our graph. 9.3, done, in the bag. I'll see you in Check on Learning.